it's recording. Are you all able to hear me okay? Because I'm trying to position my document camera and the laptop. Okay, so the plan is, Shani's here. Okay. The plan is to have an exam next Thursday, and it'll be over the last few sections of 16. I thought I should look it over before class started, but I'll post it as soon as we're done. So the part from the acid base, I'm sorry, the acidic, basic, and neutral salts, and so on and so forth. From that, you will have to review for the next exam. And all of chapter 17 will be on the exam, okay? I'm going to try to do one test, okay? I'm gonna try that. I'll know more over the weekend because I'm gonna, work it out. And I'm gonna do a trial exam, like a test exam, to see how Lockdown Browser works, and if you're familiar with, to get you familiar with the test taking. So I will have a trial exam or a test, practice test, I would say. It'll not have any, it may not have any questions from your lecture per se. It could be just, some random questions. And we'll see how that works. All right. So I'm thinking of doing the exam next Thursday at about 1:30 in the afternoon, 1:30 to 3. So all of you will have to take your test at 1:30, starting at 1:30 next week. And so I'll give you like 1:30 to 3 for the test. And on starting next week, because now that we know we're not going back to campus, starting next week, I would like to have classes on Tuesday at 9:30, and then Thursday in the afternoon for 2 hours. Okay, so we will not have we will not have like the Thursday morning class like we do. I don't want you to be overloaded with Zoom. And if anything in between I'm not able to get in through Zoom, I'll post on Canvas. All right. So everybody with me, I have 17 of you. Do you understand? Starting next week, we'll meet. I'll put this up on Canvas, and I already did last night. Starting next week, next Tuesday, we'll meet at 9:30. I'll continue with chapter 18. And next Thursday, 1:30 to 3 will be your exam online. And then I'll have a test exam that'll become available on Monday or so. I'll let you know. Okay, I'll be working on the test this weekend, so I'll have a better idea. And then we'll do Lockdown Browser, see how far we get with that. And if we are not able to get everything in one shot, then I might do like split the exam in 2 parts. Okay, so you do one part, and then we'll come back and do the other part. But I'll let you know on by Monday. I'll have a better idea. Does that sound good? So what are you going to do? Those last sections from chapter 16, I'll look that up and let you know. And or when I go to the interactive book in a minute, I can let you know what last sections from 16 you need to know, and then all of 17 that we have covered. All right. There are some more sections after the ones that I finished, 17.7, but you don't have that for the test. So all of 17 and the last few sections of 16 is what you'll have to review for your test. And I'm working on a practice test on sapling. I'll have that available. And homework 3, when is homework 3 due? Is that due Sunday? I don't remember, but it's all on Canvas, okay? And then the titration worksheet, that I know is due today. Brandon Wu, okay. Elma, what was your question about lab?
I think it was just like basic questions about lab that I had. I don't know what they're off the top of my head, but I think it was just the generic way like things are gonna go.
Yeah, so it's going to be virtual. The next one, the next lab is in your schedule. I think it's the acid-base titration lab. So we'll give you data for the lab, and then you'll do the rest of it. Like you did the buffer lab, that's how you would do it. So it's going to be virtual labs, or I might even use the activity that you used for this week's lab, the titration, and I could use that, and I could ask you to run your titration that way. And so I'm trying to get creative by the day, and so I'll let you know. So instead of me giving you data, I might tell you to use the activity and collect data and put that on your data sheet. Does that make some sense?
Yes, ma'am, that does.
Okay. And since all of you are familiar with that activity, I'll have a data sheet and we'll give instructions for collecting data. So other than being in the lab and doing the experiment, you're going to collect data and then do the experiment as usual. Francis? You had a question? Mm-hmm.
No, I have no question.
Why you, never mind. He lifted his hand and I thought he had a question.
I have a question, Dr. Mary.
Yeah.
For the lab quizzes,
Mm-hmm.
I don't know if you just talked about this. I've been kind of like writing stuff down in the middle, so.
What
the
about
lab quizzes will be kind of the same way.
They'll be online.
Right, with the lockdown browser the same way.
Mm-hmm. Yes. So you'll have one lab quiz and then a lab final.
Okay.
So that's the plan. Okay. So after you finish next week's lab, then we'll talk about the lab quiz, and then you'll have a lab final.
Okay, yes, ma'am.
Okay. So you will do the titration lab next week. So you'll have a write-up, like you'll have the theory because that lab is in your lab manual. So you'll have the theory and, like the usual write-up. And some of you, if you do not have your lab stuff, then you need to email me and I can provide that for you. So you'll do the write-up like before. We're going to have a TA meeting tomorrow, so that's when I'll be posting the information, and we'll give you enough time to do the lab write-up. Any questions about lab? So we're going to do virtual labs. We'll do as many labs as we can virtually, and for some labs you'll have a full write-up, and for some, well, there are only like 2 labs left, I think, 2 or 3. Okay. So the lab part shouldn't be much of a concern. It's going to be, you're going to do as much learning as possible from those labs. So I'm going to make it as closely related as possible to what we are learning in lecture. Any other questions about lab? But make sure you're turning in everything that you're supposed to turn in. And then please keep up with Canvas. I know you're loaded with announcements as you know, by the hour, but make a calendar and make a note of when you have to turn in what. Okay. All right. Anything else? No? Okay. Well, some are missing. Could you ask your friends to show up? They're not on here. Okay. All right. So I'm going to start. Any questions from chapter 17? And if you do, I'm going to just take the questions and maybe after 3, I will answer those. Okay? No? You'll get 100% on the exam next week? Everybody says yes. So I'm excited about that. Now I need to write challenging questions, right? Or not?
No.
No? Okay. All right, so do you see my handout here?
Mm-hmm.
Okay. All right, so this is what we are going to do. We've talked about buffers, we talked about titrations, we talked about pH, right? Equilibrium. We'll still talk about equilibrium at the end, but we are going back to, remember, what did we learn about chemical thermodynamics in the past? Anything you remember? Anybody? Chemical thermodynamics. Chemical, what about
Hey,
thermo?
Leslie, be quiet.
Kinsey, what is it?
Hey, I'm on a call.
Okay, can you mute yourself then?
No.
Okay, all right. Let's see if I can do that. Mute all. I'm going to mute you all, and then if you need to ask me, you can. Okay. All right. So we talked about, do you remember entropy? I'm sorry, enthalpy. We're going to learn about entropy. Enthalpy. You remember that? What's the formula for enthalpy? Kevin, what's the formula for enthalpy? Forgot, right? That's okay. Change in enthalpy, remember? Delta H. So today we are going to learn about another Greek term, entropy, and that's delta S. Okay. Enthalpy, H, heat, entropy, delta S. And then we're going to put all of these together, and then we have something called free energy. Delta G. Okay. Why do we need these? This has to do with heat changes. Remember we talked about exothermic, endothermic. All right. And so for a reaction, we need to know how that affects, how much of the product we are making. And this is what we're going to learn today. This is going to talk about, it's all connected. It might seem kind of odd, randomness. And how is that quantified? Okay. And this is putting delta H. There's an equation that relates delta G to delta H and delta S. And ultimately, delta G will tell you if a reaction is spontaneous or not. You may want to push the reaction to make products, right? Now we are trying to make drugs that could be a vaccine, right? So we want the product, it's a chemical, a large chemical, is how are we going to push it to make this product? Is it spontaneously going to happen? All right, so that's very, very important for any type of synthesis we do. And you will learn about delta G a lot in biochemistry. So within the body, within biological systems, what reactions take place spontaneously. And we'll also, at the end of this chapter, we link this with capital K. What is capital K? Stands for Kennedy. Stands for Kennedy. It's K equilibrium, right? K equilibrium. So we're going to relate all these guys. So it's like bringing everything together. But first we have to talk, we've talked about enthalpy, and we'll bring in some equations that we used last semester. So we'll talk about this guy, okay? It seems a little abstract, but we'll see how, these mathematically talented people, physicists, and physical chemists have put stuff together, okay? They've quantified it. So we're going to learn about these things. I'm going to move on to the next slide. So first, chemical thermodynamics or thermochemistry is what we call it. Thermochemistry. Because thermodynamics is covered a lot in physics, and we're going to learn the chemistry aspect of it. So how heat and work. Remember we talked about Q and W last year that are involved in chemical reactions and physical changes such as changes of state. Okay, that's a general definition. Now here's what we are going to concentrate on, okay? And it'll become very clear at the end of the chapter. Spontaneous. What do we call a spontaneous? Some things happen on its own under the conditions given. You see what example I have on the next page. Okay, I have an example on the next 2 slides from here, so I'm going to wait for that. So they happen under indicated conditions. So does something happen at 25 degrees centigrade and room pressure? If I bring ice from the freezer and leave it on the countertop, it's automatically going to melt. So that's a spontaneous reaction. Some are fast. Explosions, boom, that's fast. Some very slow. What branch of study is that? Reactions happening quickly or slowly? Where did we see that? What chapter?
Chemical kinetics.
Yes. Chemical kinetics. Okay. Non-spontaneous. You can beat it with a hammer. Some of these reactions don't happen. Okay. For example, if I take liquid water and maintain the temperature at 25 degrees centigrade, will it become ice? No. Okay. So you got to be very specific. Under these conditions, will liquid water become ice? Not at 25 degrees centigrade. So that is a non-spontaneous reaction. Okay. Like that. Now this is a general review of the first law, which we saw in the thermochemistry chapter. The total energy of the universe does not change. So you do not make or destroy energy, but you can transform it from one type to the other, okay? Mechanical energy to electrical, something like that. Nuclear to electrical. Electrical to chemical. All right. So we're going to learn about some of these like that in the next chapter, which is electrochemistry. Okay. And this is again a review from thermochemistry. Sorry. Is the picture clear? You have the system, remember? And surroundings. So if I'm doing a reaction in a beaker, which is, you know, what you did in lab, and you have some solution and you use a Bunsen burner and you heat it, right? So we said the chemicals in here, that's your system. And how the heat that is given off, right, interacts with the outside. So the outside of the beaker, so the lab was your surroundings. And that whole thing with the system, heating, and the whole lab, that's called the universe. Because when you have heat involved, you have exothermic reactions which affect the surroundings, and then you have endothermics, thermic reaction where you get heat from the surroundings. So in a reversible process, there's a lot of meaning to this word, reversible, and you learn more about it in physics. The enthalpy change. How will you represent enthalpy change? Delta H. Okay. Reversible here, to keep it simple, this is going to be our equilibrium process. To keep it simple. So delta H in the forward reaction, and we learned this is one of the rules. If you reverse the reaction, right, It was negative delta H reverse. So if you had a reaction A plus B giving C, and the delta H for that was positive 45 kilojoules per mole. Remember Hess's law? C now giving A plus B. What is delta H for the reverse? It would be negative 45. Not that. So that's what they're talking about. Okay, someone's still writing. Melting of ice. So this is the example that I was alluding to earlier. You have ice cubes. Those are my ice cubes. We could, right? Melting of ice. Now, you bring it out from 0 degrees, right? And then let's say you're bringing it to 25 degrees centigrade. And at this time, this is a spontaneous reaction. Do you think it's endothermic or exothermic? Any thoughts? Here, it should be endo or exo. You think it'll give off heat or it'll pick up heat from the surroundings? We don't want to think. So this is, what kind of a reaction? Endothermic, right? So the outside temperature must be higher, and the freezer is about minus 20 degrees or so, okay? And so it picks up the heat and it starts melting. What about the reverse process? Liquid. Now you're going to put it in the freezer. I'm going to make it one big ice cube. So will the reverse, of course you have to change the temperature. It has to be less than the melting point, right? For it to become ice, otherwise it's not going to, whatever you tell him to do. What's the reverse reaction? The reverse reaction is exothermic. Okay. So here, they're not asking you to go into the details of how do you know it's exothermic or endothermic. What they're trying to say is both are spontaneous processes, but the first one being endo, the reverse is exo. But they are spontaneous at different temperatures. Here, T is greater than 0. You have to bring ice to a higher temperature to make it melt. And if you want to freeze it, it's going to be at a lower temperature. Okay, this is exothermic. Any questions? Okay. All right, we are good so far. Now, other reactions I said, you can beat it with a stick, but it doesn't happen. Combust gasoline. Okay, I'm going to take one component, butane, okay, plus, remember our combustion reactions. What are the products? CO2 and water. This is combustion. And this is spontaneous as long as you provide a spark, okay? That's what happens in our cars, gasoline. Ignition, right? When you turn on the car, then it starts the process. Now, this is spontaneous. Now, we have a lot of CO2 and moisture in the air. Okay, does it become gasoline? Everybody wishes, right? Then I can make some CO2. I can make some gasoline in my backyard. But this is non-spontaneous. So that's why we have to think of spontaneous. That's why we have to think of other means to make gasoline, right? So we talked about enthalpy and spontaneity, okay, as we understand it so far. We're going to the next slide. Second law of thermodynamics. Here's where we introduce this term, entropy. Spontaneous processes always result in an overall increase in entropy. Okay. Now, what is entropy? Degree of disorder. How do we measure that? Okay. So degree of disorder. Let's say right now I say, okay, class dismissed. I'm not going to say that, okay? We're going to pretend. And you will be all going in different directions. Well, you can't go much today, unless you all need to go to the grocery store or something, right? Fill gas. Adrian will go elsewhere. So that's, how do I measure that? How fast do you run? Or how quickly you all dissipate, right? That's the question that scientists have, and they had at that time, and they try to quantify it. I think that's a big task. All right, degree of disorder. Another example would be, let's say you spray some cologne or perfume. Those molecules were in a bottle in a liquid form, right? And then you go, you spray it once or twice. What happens? All of those guys escape as gas and they fill the whole room, right, for a while. So how do you measure that degree of disorder? Do you see that? So that's, you know, but that's where math has come in handy to help them. Another way to think of entropy is how spread out a system's energy is. Okay. How do you measure that? So they have taken large steps, but for us, they're going to explain it in a very simple manner. And we learn a little bit more about that in physical chemistry, right? Like we talk about microstates and things like that. It's going to come soon, but I'll point that out at that time. So factors affecting entropy, okay? So this is baby entropy class. Factors affecting entropy. Solids are highly organized. Okay. A picture of the solid. And if you look at your textbook, it's a nice colored picture. I still manage to include it here. Solid, in a solid, you see how these atoms are arranged in a very regular pattern, and the atoms are very close to each other, okay? Atoms are tightly held in a pattern. Okay, that's solid. Tightly. Okay. What happens when you heat the solid? Okay, we're not talking about temperature here, we're talking about entropy. So the solid has to be heated, right? To melt. What happens in the liquid form? You think about ice and then liquid water. Liquid water, I can, you can make it flow. And so the molecules are less tightly held. So is the degree of randomness increasing or decreasing here?
Increasing.
Increasing. Thank you, Ralph. So the degree of randomness is increasing. Okay. I mean, qualitatively, that's how we say it. So how do you represent this? We say the change in entropy, this is what we're learning, new here, the change in entropy is increasing. Okay, the change in entropy is increasing. And how do we represent that? That's the sign here. You see that? Delta S is greater than 0. Delta S is a change in entropy. Okay, so you'll have simple problems like this. And so if the degree of randomness increases, then you say the change in entropy increases. Okay, and this means the change in entropy is positive. Change is positive. Remember, delta H positive means it's endothermic. If a reaction is exothermic, then delta H is negative, remember? It's the same thing. So try to remember the signs and the signs, okay? Now, as we go on from liquid to gas, that's a big change, right? These guys are like, I don't want to be near each other, right? And they are spreading. So degree of randomness increases. Okay, if delta S, okay, I'm just theoretically giving numbers. Let's say delta S is positive 20 here. The change, delta S here would be positive 2,000. You see that? Solids, they just break up a little bit to become liquid. Now the liquid, when you heat it, like water, when you heat it, you don't know where those water molecules are going, right? Could be all over the kitchen and into the dining room. So that is a greater spread. Totally trying out. So here, again, delta S is positive. Okay, you get the idea? Now the reverse, okay, pay attention to the reverse. If you try to, what do you call this? Going from gas to liquid, what's that process called? Gas to liquid, liquid to gases, vaporization. Gas to liquid is condensation. I'm not going to write too much more on the slide. It's already crowded. Delta S is less than 0. So delta S is negative. Then going from liquid to solid, what is that process called? You can say crystallization or fusion. Okay, delta S is negative. And this is, what type of a change is this? Chemical or physical? It's a physical change, right? Because it's still water. It's not a chemical change. So we've only looked at an example of a physical change, but it's still, you know, the process is the same of understanding how randomness increases and how we estimate delta S and so on and so forth. Okay, everybody good? Okay. Now going back to where I was. Let me look at slide number. So going back to slide number 9, kind of jump the gun here. Okay. So I explained a lot more than that was needed for this slide, but solids are highly organized, liquids less so. Gas particles move randomly. So going from solid to liquid, delta S is greater than 0. Going from liquid to gas, delta S is greater than 0. Okay. So now an increase in temperature, what will it do to randomness?
Increase.
Increases. What does it increase? It increases the kinetic energy of the molecules. Okay. And so the particles will start moving faster, more rapidly. And then the entropy will increase. Okay. KE is kinetic energy. Okay. All right. Now specifically talking about when you talk about kinetic energy, you're talking about gas molecules and solid in the liquid also, they can move. An increase in the kinetic energy and the movement of gases will increase, allows for the energy to be more randomly dispersed throughout the sample. Okay. Energy is more randomly dispersed throughout the sample. And this is what we're going to look at next. An increase in the number of particles. Okay. What if you increase the concentration of gas molecules? Provides more ways for the system's energy to be distributed. Okay, so here's where they came up with a mathematical model. Okay, and they talk about microstates and macrostate. We learn a little bit about it. Your textbook introduces this chapter, this section. Okay. And we'll just scratch the surface of the problem and learn a little bit about it. Okay. I think we're going to do a problem next. Okay, I'm going to give y'all a minute to come up with possible answers for this problem that I have on the screen. Now, if you have a solid going to a solid, and if you have 2 moles of this giving 2 moles of that, and think of it as not much of a change happening as far as solid to solid goes. But think about here, a solid is also becoming a gas. Okay. And then a gas here becomes a solid. And here, look at the phase changes. Think about what condensation means. Got it? Sort of. Okay. What do you have then? So you have to give the sign for delta S, okay? I want you to give the sign for delta S. So what is the answer for the first one? Is the degree of randomness increasing or decreasing?
Increasing.
So I like to do that. And if it is increasing, what's the sign? Greater than 0. And also note on the side that it means positive. Some of you had it confused for delta H. So I want you to keep in mind, if it's positive, then delta S is greater than 0, right? What about the next one? You're going from gas to solid. What about the degree of randomness? Does it increase or decrease? So delta S will be negative. And the next one, looks like it's going from solid to gas. Right? That's how it looks to me. So increases. And then this is greater than 0, positive. Condensation. Again, I mentioned the term earlier. What does that mean? Condensing. So you have gas, okay, water vapor becoming liquid water. So gas to liquid, is it increasing or decreasing? Decreases. Everybody understand? Delta S, if it decreases, it's going to be less than 0. It's negative. Okay. All right. All of you got A's on this quiz, right?
Hmm.
Any questions? No question. Everybody's like, come on, hurry up. Summarize. A phase change from positive value. Okay. See, I erased everything. Going from solid to liquid. And a phase change from solid or liquid to what? Gas. Now dissolution. So I take sodium chloride, and if you put that in water, delta S increases. Okay. Increase in temperature within a phase. So if you are having something in the liquid phase, and if you increase the temperature, then delta S is going to increase. So all of these for a positive delta S. And this is what we're going to talk about. The microstates increase in the number of particles or increase in concentration. Moles or molecules per liter. All right. This is so much better than doing those calculations, right? For buffer. Okay. Next, we are going to do a little probability. Ooh. A little bit of math. Sorry. I talk, my throat's getting dry. Let me turn down the heat. Okay, everybody ready for the next one? All right. Entropy and probability. Some of you must have had probability and statistics, right? Entropy increases when there are more energetically equivalent ways to arrange the components of that system. Okay. Now we're going to see how they model this, and that will be only a small part of, how we look at the system. Okay? So it just gives you an idea as to how they set it up. Entropy was defined mathematically. Okay. Here's where they went from something that's abstract, according to me, like how do you measure the degree of randomness? And Boltzmann in the 1870s, he had a lot of time, so probably was stuck home for something. And then he came up with this equation. S stands for entropy. Okay. They are always, even in the it's in the charts, it's easier to measure the change in entropy rather than actual entropy of the system. But mathematically, with some assumptions, I would say, they came up with an equation. K, it's not the rate constant or the equilibrium constant. It's after Boltzmann. So it's the Boltzmann constant. So if it's given in this equation, then that's the Boltzmann constant. W, number of microstates. We'll see what that is. We're going to look at very simple examples. All right. Got it? Now, how did he come up with Boltzmann, with the value for Boltzmann constant? He did a very simple thing. Remember our gas law constant in joules? What's the value? Anybody remember? Joule per Kelvin per mole. And so that is for 1 mole, the gas constant. So he made that for every molecule or atom. So he divided that by Avogadro's number. Per mole. So he ended up with this. Then he attached his name to it. And there it is. Okay. 150 years later, we're still talking about it. W, that's what we're concerned about here. What do we mean by a number of energetically equivalent arrangements? Okay. Let's say I have 3 stands or tables. How am I going to arrange? Let's say I have 3 boxes. Okay, I put 1 on each stand. What if I have 3 stands and I have only 1 box? Right? I have 3 boxes, 3 stands. I have 3 stands, but 1 box. So here I can put the box here. The next scenario, I can put the box here. Put the box there. You see that? And these 3 stands are at the same level, so they are energetically equivalent. Okay. The analogy works that way. And so I get 3 microstates. Here, if I have 3 boxes and 3 stands, I get only 1 microstate. if I can only put one box and one stand. Okay. So this could be our molecules. How do we arrange the molecules in the space given? And they say the number of equivalent microstates makes up a macrostate. This is basically what they're talking about here, but they're going to give us examples so to make it a little bit more clear. Got it? Okay. Now this is an example. You could look at it in your textbook. It's probably a little bit more clear, the diagrams. So you have a container, let's say a fish tank or something, and then you have a divider in the middle. So it doesn't allow any particles to go to the other side. And so you have all your particles, how many ever there are, we don't have to count it. They're all in one corner, right? Now, what happens when I remove the divider? These guys are like, I'm let out of jail, you know? They try to run and occupy as much room as possible, right? So it's like us. We're all confined now. And after the rule is removed for stay at home or the law, then we just randomly move around wherever we want to, right? Now, is this a spontaneous process? When you lift that divider, you think the molecules will say, no, I'm just going to stay in my corner? No, right? So this is a spontaneous process. Human behavior is the same. I wouldn't want to, right? I'd want to move. And if you spray your cologne or your perfume, will the molecules all say, oh, I'm just going to be around you all the time? Okay, then we will not be spending so much money on perfume because we're going to have the smell for a longer period of time, right? But it doesn't. It just dissipates more quickly than we want it to. Okay, so if I have a container and if I have particles all over, I cannot tell the particles, hey, go find your corner and do your homework. I have to put something down for them to stay in that corner. So without the divider, this does not spontaneously go to its corner. Okay, that's how it is. So scientists, okay, all the creative people who know math and physics and chemistry, okay, they try to explain this phenomenon to derive, mostly it was physics and mathematical relationship. Okay, so they always like to have a challenge, and when you do that, lots of assumptions are made. Okay, and mostly it'll work for simple systems, but they have a relationship in place. Unless someone else comes and disputes that, we are still going to learn this. So a little bit of probability. You have a box. This has a divider, okay? So A can be only on one side of the box. Like he cannot cross over, okay? So consider a box like the one shown here. there's a divider in the middle, and so two possible locations. There's only one gas molecule, so it's like the pot, right, and my stands. So he can be here, and another time he can be there, because this divider I'm going to, it's not A. It's available to A to move, but he cannot go from here to there, okay? If he's here, then he can go down here, but if he's here, he can go up or down. So it's like a townhouse, you can go up or down, right? You sometimes up on top and sometimes on the lower level. So how many positions are available? 2 positions. Not 4, but 2 available. And there's only one particle. 2 possible arrangements. That is our W, and we call those, or we will be calling those microstates. Okay? The possible arrangements are microstates. Right? So it doesn't matter how many particles or how many positions they can go to. It's like how many arrangements are possible. So we have 3 variables: particles, locations, arrangements. Okay? Particles, locations, arrangements. You need to keep that in mind. So here you have A and B, and again the same rule, they cannot go to the next house. Okay, let's say this is a duplex, they stay here. But you have 2 people in the house. So A can be on top, B on the bottom, B on top, A on the bottom, A, B, same room, A, B, same room, but lower level. See that? It's like I'm seeing you all in different places, right? Mostly one person, one location. So how many arrangements are possible? Okay, so you have 2 particles, 2 locations. How many microstates or how many arrangements? 4. Can you come up with a formula that will relate W to number of particles and number of locations based on the previous example and this example? No? Any Boltzmanns? No, you don't want to think too hard. Have you all forgotten how to think hard? Okay, go to slide 21 if you're working with me through slides. This is the relationship. Okay, that's why I was trying to isolate the 3 variables. X is the number of locations. N is the number of particles. Okay, again, a formula like in statistics. So if you have 2 locations, 2, 1 particle, that's why in the first case we had only 2 arrangements. The second case, we have 2 locations, but we had 2 roommates, right? So this was 4. We're going to look at the third example, and you're going to have 4 locations. So we're going to open up the divider and still only have 2 particles. So 4 locations, 2 people, so that is 16. Got that? So these are the values for W, and these are what we are going to call as the microstates. Okay, so that's why, if you remember, let me go back to that slide. Summary of increases in entropy. Remember we said increase delta S is 0, or entropy increases when the number of gas particles increase. Why? You see here, when you have one particle, the number of microstates is 2. When you have 2 particles, the microstate is 4. You see that? And here you're changing the number of locations too, so not just the particles, but I wanted to point that out to you. Now let's look at their example. So I think I'm going back to this is slide 18 that I showed you before. 2 particles, 2 locations, 4 arrangements possible. Next, they're going to remove the divider. So the 2 particles, okay, so they also bought the duplex next door. They have 4 possible locations. Okay, so you can play a game, and let's see how it's arranged. It's down here. Okay, this is the second example. Two particles, 2 locations. The dividers are in place. 2 particles, 4 locations. So dividers are removed. And so look at it, there's lots of permutations and combinations. A, B, B, A, B, B, A, B, B, A. Then put them together. There, and then across, okay, and then flipped, and then that and that, okay. So for me, it's easier to do the calculations and say this is 16. Okay. All of those possibilities are true. Okay. Now, bit of theory. I kept pushing the term microstate so you'd understand it for this slide. Each possible arrangement of particles represents a microstate. And then if you have 16 microstates, then you have a macrostate. Okay, macrostate is the total number of microstates. So which macrostate will the system prefer to have? The system will prefer to have the macrostate that has the most number of microstates. Okay, that's the fundamental understanding. So that's where I'll let you write it. Got it? So that's why, and they understood this about any system, okay? That's the natural response will spontaneously move to a more spread out arrangement, okay? So that's where they try to relate spontaneous or spontaneity related to disorder or randomness, okay? Qualitatively, that's what they found out. And therefore, the conclusion disorder is then, this is how they try to make it mathematical. Disorder was preferred. So what is the statistical? Okay, so it became a statistics problem. How do we figure this out? Quantify it. Okay. So now, if you decrease the number of locations, okay, if you say the particles, there are 2 of them, if you want them only to the left, then they're going to use 4 of the 16 available microstates, right? Because W, there are 2 particles and 2 locations. So you are limiting how many places they can go to. And here, you want them on the right only. Again, you have 2 locations and 2 particles. This one, you have 1 particle on the right. Again, you're making restrictions, and you want 1 particle on the left. Okay. So here, my neighbor's dogs are barking. So you have, these are spread out. So you have 2, the A and the B here, or the B and the A. They're not to stay together. And A and B, and then B and A, across this way, across that way, across this way. So they use up about 8 of the microstates. So now they've given you a problem, and I'm going to give you time to look at this. Particles are on both sides here. And then you have particles only on the left. Okay. And they want you to predict the sign of delta S. So what you should do is calculate how many microstates are possible here, how many microstates are possible here, and there's no divider. Okay, there's no divider. And so I'm going to let y'all think about this, and I'm going to post the answer when I upload this file. Okay, so I wanted y'all to think about it. I want y'all to think about the examples that we've looked at here and have a good understanding. So your questions will be as simple as that. Okay, but I want y'all to, everybody to think about it. And since I cannot stop and ask questions, I'm going to leave this as homework. And I can even upload a separate file with work shown for that. Okay. Now we are going to the next section. So that's all you need to know about that. The formula that you have, and then if there are restrictions, how do you create the microstates and be able to do simple problems like the example that was shown. Okay. Any questions so far? No. Let me look at the time. It's 51. I'm going to keep talking to everybody for another 10 minutes or so, and then I'll stop and ask questions, and then I'm going to continue recording, and after 3, you don't have to necessarily stay, but I'm going to make some announcements right at 3. Okay, is that good? I just want to get into this. Everybody okay? If somebody's not okay, just lift your hand or something like that. Or there's a chat here. Will is gone. Where did he go? Will is here. Okay. Hello, Will. All right, let me continue. And for this, we're going to do problems like we did with delta H. So this part is not difficult, but I would suggest entropy and temperature. Okay. To do this, I pulled out slide 29. Okay, a table like this. If you don't have the PowerPoint, so look it up on Canvas. It's table 18.1. It'll be useful for problems that we do. So Boltzmann went and did whatever he did, and we're not going into more details about microstates or macrostates. We're going to look at simple equations that helps us look at the bigger picture. Okay. But when you take a PChem class, we'll be looking at those again. Okay, microstates and macrostates.
Hey, Dr. Mary.
Yeah.
Before you start on this new section,
Huh?
I'm confused on the homework question.
Oh, what about the homework question?
So, do we do where like we would calculate W where A and B are only on both sides? So we would do A and B and then B and A and then the same for the top.
Mm-hmm.
And then on the other one, it would be like only 2 because they both have to be on the left side.
Yeah, yes.
Okay. Thank
Yeah.
you.
So they've given you restrictions. So they're saying these 2 particles can be on both sides, which means they can be here, 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 here. Okay.
Okay.
And then the particles on all particles on the left. So these guys, they have to be here.
Okay, but they don't have to be in the same box.
They don't have to be in the same box.
Okay, thank you.
So I think I'll so try as much as you can, and then particles on both sides, all particles on the left. Why don't we? So that's why the restrictions need to be clarified. I'm going to say all particles on the left. So I'm going to say they don't have to be together. Don't have to be together. Does it make sense? all particles have to be on the left, but you can have one up on top, one up on the bottom, and then two can be here and two can be there. So how many do you have? 4. You see that? This is slide number 24. They don't have to be together. And here, they can be together. So simply draw out, you know, how is that possible? Like how they drew this thing out for you.
So should we have them labeled as A and B so we can flip them, or are they just the exact same?
No, label them as A and B, please.
Okay, I see.
So draw boxes and then see which one has a larger number. Oh no, you have to see going from here to there, if delta S is going to be positive or negative. So let's say this has a larger number. This is smaller. Going from larger to smaller, is delta S positive or negative? Let's say W is larger, W1, and W2 is smaller. Going from this to that, will delta S be positive or negative? Going from larger number of microstates to smaller number of microstates, delta S will be negative. Or delta S decreases. Does that make sense?
Yes.
Okay. I don't know if this is going to be larger or not. I think it will, because you're restricting this guy and you're not restricting this. You see that? You have to find out how many though. Is that more clear now? Your task? Good. So I want you to review all these box diagrams and then think about the problem. That's why we're not doing it right away. Any questions about them? Are we at the 3 o'clock mark? Okay, 2:58. All right, I'm going to continue. I'm going to do at least one more section. This should go faster, I hope. But I'll be recording, so you will have it available soon. So next week, and I'll be posting more announcements about it, we will meet. I'm going to write on here. Okay, announcements. Next week, we will meet on Tuesday at 9:30, okay, till 11 a.m. And then also we will meet on Thursday. Well, we'll not meet, but I'll be available on Zoom at 1:30. You will take your exam then. Okay, from 1:30 to 3. And trial exam on Monday. Okay, I'll have the times open for this. You can take it whenever you'll be testing how to use the lockdown browser. And the math editor. So I'll give you mathematical problems. The math editor has formulas, and you can use the calculator, I think. So that's where you'll show your work. So we're going to try that. And then we're going to test, like I'll give you a titration, uploading a titration worksheet, titration table. Because remember, for doing the doing the titration problems, you were given a titration table. So I'll have those tables available to you ahead of time. And then for a particular problem, you'll have to fill those out and upload it. So after the exam is over, I'll give you about 10-15 minutes to upload the titration table. You'll have to take a picture and then upload it, like you've been uploading your assignments. Okay, so we'll be testing those. Trial exam on Monday. And in the meantime, I will be preparing the exam. And then for some reason, if I feel maybe you should take the exam, I don't want to do that, get it all done in one shot. But if for some reason I'm not able to, then you will take the exam in 2 parts. But your first part will be next Thursday at 1:30. Okay. And then from the week after, again, we'll meet Tuesday at 9:30 and Thursday at 1:30. So Thursday morning, we'll not meet at 9:30. We'll just do one big session in the afternoon. And how many chapters do we have left? Well, we have chapter 18, which we are on, chapter 19, and chapter 20, parts of it. Okay, so 18, 19, and 20 are not like 17. They are shorter chapters. So there will be, like 18, I can be finished with 18 by Tuesday. You see what I'm saying? So these are not, 19 may be a little bit longer, but nothing like 17 or 16 even. Okay. So I think we've crossed the transition state for this class. We are moving along, okay? Fine, I think. So that's the plan. And lab, like I said, next week, you will do a titration lab. Let me find another scratch paper. I don't know what what experiment that is, but this is the acid-base titration lab. Okay, acid-base titration lab. And then you will have background, procedure, of course, equipment. And then for the data table, we'll give you instructions. You'll collect data using, what's that figure 17, 14 or something that you use for the titration. Okay, instructions will be given. And then, so you'll be you'll be doing this, and then you will turn in your, of course, you'll do your pre-lab. And then you'll submit your data table, and then you'll have post-lab. Now, you will not be doing all of this in one shot. So you may be doing this, okay? Part 1. And then you'll be doing that, part 2. Got it?
So we're using the same interactive for both labs,
Yes.
both this week and next week. Okay.
Yeah, but I'll give you, that's a very good tool that we have. So I can tell you, I'll give you instructions, I'll say, and you will do a weak acid, strong base titration. Is what you will pick. And I'll also tell you which indicator to use. And I'll say, add 1 drop of sodium hydroxide, write down the pH. All right, not 1 drop, 0.1 ml. Or I'll say initially you can add 1 ml at a time. And then after you've added 10 ml, add 0.5 ml at a time. You see that? So you'll see in your data sheet, and that's what you would have done in lab as well. Like you will add a certain amount and then you'll record your pH and write down the pH. So you'll do that with this interactive figure that you have. Okay.
Are we getting the background and procedure and pre-lab and post-lab from our lab manual that we have?
Yes, you'll use your lab manual for that. And I don't know what experiment number that is, but we will post that on Canvas. I think I'm meeting with the TAs tomorrow, so it'll be tomorrow. But you have a heads up about what you need to work on. All right. And I wanted you all to do the post lab, but because I think that will be a review for your exam as well. But some of you may do it, and some of you, because I'm going to make this part due first. Okay, so you have enough time to work on it, and then that part will be due next. And I'll give you enough time to do it. Does it sound like a plan? And then also for electrochem, we have interactive stuff, from chapter 19 to do your experiments. So I'm not worried about your labs. You're learning just as much, or in some ways you're learning more from it. But the only thing that's missing is the hands-on, experience. So, which, I'll take care of that next year when I see it in my classes. So I know that's, but there's lots of students who are taking online chemistry classes even otherwise, and sometimes they have virtual labs, and I think they learn a lot from it. Because each piece of equipment, when you go to use it, it's like your microwave, your microwave is different from my microwave. So there's a learning curve there. So it's something like that. It's like, how do you know the analysis? Do you know how to analyze the data? Do you know how to relate that to concepts learned? And so that's, I think, is more important for learning. I think there are chat questions. Okay, all right. Class distance. Okay, so I'm recording the whole thing. So if you have problems with your connection, then you can see I've been recording it ever since 1:30 p.m. And and I'll keep recording the information, so you will have it, even if there's a problem with the connection. Anything else? Okay, so I'll keep rolling for a little bit until I get tired and feel hungry. And what are you doing for fun these days? Sleeping? No fun, Maddie?
No.
Oh. Just reading Canvas announcements and doing homework. Yeah, I'm busier than usual. I'm trying to learn a lot of stuff.
I had to write 2 papers yesterday, so
Yeah,
I was a little busy then, but
yeah. Oh. All right, let's look at this one here. Entropy changes.
Okay, man.
Oh, yes, question?
Yeah. Do we have to wear long pants for labs too?
You have to wear lab coats? What did you say?
I said, do we have to wear long pants for labs too?
Yes. Wear goggles, gloves. I don't know if you can find gloves outside, but yes, Kevin, all of the above. Are you prepared? All right. We're going to state the third law of thermodynamics. And I'm using a black pen because Will wanted me to use a black pen. And we'll calculate delta S. Okay, so we'll finish with this section. Okay, so we learned how to predict the sign for delta S. Third law of dynamics. Okay, it actually depends on entropy. The entropy, so here are some of the assumptions or restrictions they make. The entropy of a pure, perfectly ordered crystalline substance, because nothing is moving there, okay? And it's an absolute zero, all right? So if they take a crystalline substance and bring it to that low a temperature, 0 Kelvin is what in centigrade? Negative 273.15 degrees centigrade, okay? So they're saying everything is like not moving. So they clarify or they assign a value of 0 for such a system. So everything comes down to 0. At absolute 0. There's no thermal energy. And the particles in a perfectly ordered crystal would exist. Oh, there's only one microstate. Okay. So when you have one microstate, what is the value of S? When there is one microstate, what's the value of S? What is W if you have a single microstate?
1.
1. So what is S when W is 1?
1.
What is ln of 1?
0.
So S is 0. Okay. So there's no randomness when it's that cold. They all are in just one microstate. You see that? There's no randomness. That's what it means. Okay. I did cryotherapy for my back, and that temperature was the boiling point of liquid nitrogen. So it's like minus 170. But this is minus 273.15. Okay. Now here comes a formula. And they're referring to this table. S0, okay, if you look at the table, you may need this. Slide 29. Tabulated entropy values.
Dr. Mary,
Yeah.
Mackenzie Burt gone. BT Dubs. She got kicked out.
Who? Kinsey?
Burt. Yeah.
And she wants to come in?
Yeah, she do. She do.
Okay, she needs to,
She needs to join back in?
yeah.
All right. Got you.
Adrian, how do you do that? Could you help Kinsey get back in? I think you have to join back in.
So I think that she's going to have to try to reconnect her Wi-Fi, and if that doesn't work, then
Mhm.
she'll be completely like the Zoom session, unless you let her back in. But if her Wi-Fi doesn't work, you letting her back in is not going to work.
Okay. Did you get that, Shani? Okay, I'm admitting her. Kinsey is back. Okay, Tom had a question. So when will practice be available? Monday? I'll give you a lot of time to work on it. And the assignment, the practice may not be more than 15 minutes long. Okay. So, and I'll let you know on Sunday. And I'll give you, enough time to work on it. It's just a practice, so I'm not worried about, I'll give you all enough time to do it. Okay, we have a new message. Will and Brandon, will you stop? Okay. All right. Kinsey's in, right? Okay, I see 20 now. Okay. All right, so S0 will have units of joules per mole per Kelvin. And again, the standard thermodynamic conditions, you remember? STP, thermodynamic conditions. 298 Kelvin, 1 atm, pressure, 1 molar of solute concentrations. Okay. How do you calculate delta S0 reaction? This is the coefficient. So you add up all the the product for the, multiply these two for all the products, and then multiply these two for all the reactants and subtract the two. Okay, that's sigma, which means sum of all of those things. And then we'll use a similar equation for delta H. Okay, let's do a qualitative problem. Predict the delta sign of delta S and calculate the standard entropy change associated with the reaction of gaseous hydrogen and gaseous oxygen to form water vapor. Okay. So what is delta S? And we have, I'm going to show a balanced equation. Okay. Now, can you predict the sign? They're all in the gas phase. So how many total moles do you have? Total moles is 3. 3 moles to 2 moles. So delta S, is that increasing or decreasing? Degree of randomness. Decreases. Okay, because the number of molecules decrease. So delta S then is negative. Now we are going to do the calculation. We know the sign, but we'll get a magnitude for delta S. So the next slide has the equation. We're going to use that formula. It may seem like Greek and Latin to you, but we'll see, we'll break it down. You consider the products first, okay? Because it's delta S, so products minus reactants. We have only one product. We must use the coefficient. So I have 2 moles of water in the gas phase multiplied by S0 for water in the gas phase. And then I have only one product, okay? And then I have 2 reactants. So open up a big box bracket. 2 moles times S0 for H2 gas. And then within this, okay, within that, I'm adding these 2. 1 mole of S0 for oxygen. Okay, now whether you have elements or compounds, you have S0 values. So look at the chart. Okay, and then write down the appropriate values. So I have 2 moles S0 for water in the gas phase. Okay, there's one for liquid, there's one for gas. For gas, it is 188.8 joule per Kelvin per mole. Minus 2 moles S0 for hydrogen gas, 130.7. There should be a bigger table, the appendix or something like that. And then we'll put smaller brackets, plus 1 mole times standard entropy for oxygen, 205.2. And then close it up, okay? All the reactants must change sign. Can you do the problem? Tell me what you have. You have a negative sign for delta S0 reaction because you predicted it to be negative at the beginning. And remember the mole and mole cancels. Whoever has an answer, can you give it to me?
Negative 89 kilojoules, negative 89 joules per K times mole.
Okay, negative 89.0.
Yes, ma'am.
Well, I'll tell you how many sig figs you'll need. Yeah. Joule per Kelvin. Do you get this answer or you get something else, the others?
Is there
I got
anything
that
else on the
answer.
page?
Hmm?
Is there anything else on the page? Like any other writing?
It's not showing.
Okay.
So you see, we predicted it to be negative. There it is, negative. Okay.
I have a question.
Yeah.
On the test, like if we're able to use like the delta S0 like chart, will we have to print that out ourselves? Like, do we have to go through the notes and find that, or will you like give us all the stuff we can
I'll-
use that we can print out?
Yeah, I'll give you all the stuff you need.
Okay.
Yeah. So I'll post those things ahead of time. Okay, Jessica, if you've not already left, bye. She has Spanish at 3:30. Okay. Space. Let's do another one. You see, this is not too crazy. Predict the sign. So this is, it's a physical change. It's not a chemical change. You have mercury. What we see at room temperature is liquid mercury, and it's becoming a gas. So what's the sign? Degree of randomness increases. So delta S is positive. And the values are different, right? For S0 liquid and S0 gas. So they want you to calculate S0 reaction. Same formula, there's only 1 mole. So you have 1 mole times S0 Hg gas. Always products minus reactants, otherwise your sign will change. Now, can you introduce the values? 1 mole times S0, careful, gas. Write down the units. I already see that it's going to be positive. Now remember, we have to go back and take care of this. Okay, so we've done only part of the problem. Anybody with an answer? Okay. Now this is per mole, but we don't know how many moles they have. Everybody okay so far? Anybody have questions?
Yes.
You have questions or you okay?
I have a question.
Okay, yes.
So wouldn't the moles cancel out then? Like at the end, it'll be just joules over.
Yeah, yeah, I know what you mean. Yeah. So there are the entropy changes for physical changes are calculated the same as for chemical changes. Use 1 mole of the substance. There's a lot of theory here. Behind this. And again, we talk about it in physical chemistry. Okay, so again, if you think about it, we did get joule per Kelvin, but if you look at the equation, the change is for either 1 mole of this or 1 mole of that. So this is like we did delta H calculations, and we'll write on the side delta S0 is plus 99.1 joule per Kelvin. And what that means is it could pertain to 1 mole of this, or it can pertain to 1 mole of that. Okay? So you look at the stoichiometry of the equation. I know your question, but there's not enough time, and so these textbooks don't really talk about that, but we do talk about it in PChem. Okay. So for now, assume that you have number of moles of mercury Okay, convert grams to moles. And you have 200.59, I'm going to give it to you, gram of mercury for every mole of mercury. Calculate how many moles you have. So we say this is 99.1 joule per mole. They do say mole per Kelvin. And divide by the number of moles of mercury. And tell me what you get.
Where did you get the 72.85 from?
Look, read the problem. Look on top.
Oh.
Here, 72.85 grams of mercury.
So the answer that I get is 272.87.
How many moles did you get?
0.363.
Mhm.
0.363.
Okay, so take that out for a second. 99.1 joule per mole. I should multiply it, right? To cancel the mole. You should multiply it and not divide.
Yeah.
Yeah.
I'm-
I made a mistake. I saw the mole and I thought, yeah, it should be on top. So this will give you a smaller number.
Yeah, that's 35.99.
Okay. So I'll say 36.0 or 35.99 is good. Okay, please make a note that that's not right because you have joule per mole, so you have to multiply by moles. So this is for 1 mole. How much is it for these many moles? Are you all ready for another section? Or at least part of it? So the question is about lockdown browser. If you are under lockdown, then the only thing that'll let you use is Canvas. Okay, so you can use Canvas to do the exam, the idea is that you take an exam like you do in class. Okay, so the idea is that you just have the materials that are given to you, and that's the purpose of the lockdown browser, that you have minimum outside sources. So this is not a open book test. Okay. You don't need a printer. Oh, you mean if you don't have a printer, how do you print your? You can take a handwrite it. Yeah. So you have to handwrite your equations, if that's what you're asking. I understand your question now. Yeah, there will be equations that you can use, and you can. I suggest that you write it out. Unless you want me to mail you something, you can send me your mailing address, and I'll get that to you. Okay, that's an option. Does that help, Will? And what time are we going to? I want to finish the recording so you don't have to be here with me. Okay, and I asked if I can do another section, and after 3, none of you are required to be here. I'll just post the recording and have that available to you. Can you open multiple tabs within Canvas when you're under lockdown browser? I haven't done it myself. Anybody who's done it, can you answer, Will?
When
So
you're in
the
lockdown
lockdown
browser,
browser, the lockdown browser is really basically you just go on like Google, but it's that's the only thing that your screen can do. And when you log on, it asks you to turn off certain programs that I guess are running simultaneously with it. So it's the only thing you see on your screen, and you can't minimize, you can't zoom in or out of anything.
So that's the exam screen is the only one you can use, right?
Yep.
Okay. Will, do you get that? And we're going to test it out. That's why the practice test on Monday. So we're going to try all these things. And I'll even like put up a few equations and see if you can handwrite it. Okay. Olivia also says you can't. Does that an answer? Those are all good questions. Okay. All right, let me get started, and I'll wait till I'm the last one standing. Okay.
Have a good day, Dr. Mary.
All right, bye. Take care.
Bye, Dr. Mary.
Kevin, you're leaving?
Yeah.
Okay.
Bye.
Bye. Bye. Bye, guys.
Bye, Dr. Mary.
Bye. See you all. Elma.
Hi, Dr. Mary.
Bye. See you guys. Were you able to register for your classes?
Yes, ma'am. I worked on it, but there were still some things I needed to get fixed. So
Okay.
Well, I talked with what's his name, my student success advisor, but I haven't talked with Dr. Dewar yet.
Okay. All right.
So I'm waiting to hear back from him.
Okay. So if you're going to stay on, then I'm going to start continuing, because I don't want to be recording stuff that's, but if you need to leave, that's fine, okay?
Okay, Dr. Mary.
Uh-huh.
Bye.
Bye. Maddie and Will. Okay.
Yep.
All right. Special lecture for the two of you. Okay. Entropy and temperature. That's the next section. And I'll try to keep it short. I may not be able to finish all of it, because I'm going to run out of steam pretty soon. So here we're going to talk about delta S universe. delta S system, and delta S surroundings. Okay. Oh, I should also remember that I have a TA meeting at 4. Okay, so I'll just start and then we may have to stop. I forgot about that. Now we've talked about system and surroundings. So system plus surroundings makes your universe. Okay. So when talking about the entropy change, delta S universe is the sum of delta S system and delta S surroundings. Now, what must delta S universe be for a reaction to be spontaneous? That must be positive. Okay. So if you say overall your system is spontaneous, then delta S universe must be positive. Okay, so we are going to look at when delta S is positive, right? So it's like A equals B plus C. When is A positive? What are the options? When both delta S and delta S surrounding and system are positive, right? So if you have +4 + 3, that's +7. First condition. Secondly, you can have delta S system is negative and delta S surroundings is positive. Which must be bigger now? For delta S universe to be positive, delta S surroundings is greater than delta S system, right? Mathematically. If this is -4, this has to be greater than -4, right? Let's say this is -4. This must be +5 or more. So delta S surroundings must be greater than delta S system. And then the third condition, delta S system is positive and delta S surroundings is negative. And what must also be true? And delta S system is greater than delta S surroundings. So it's simple math. When you add those two up, you should get a positive value. That's all they're saying. Isothermal. That means you're not changing temperatures. And if you do your experiment in a lab setting, as long as you're not heating anything, you're doing it at the same temperature, okay? So when you're heating it, it's no longer isothermal, temperature is changing. And also your system, right? The beaker is much smaller than the surroundings, which is your lab room. So enthalpy changes in the system, delta H system, have a very minimal effect on the temperature of the surroundings. Systems that cause no temperature changes on the surroundings are known as isothermal processes. Okay. I'm going to stop there only because I have to get ready for my meeting. And so thank you, both of you, for being there. I'll invite you all when I do my other recordings without the class and see if you want to participate. All right.
Alrighty.
I think Will has a question. I'm
He's
just
saying
trying
he's trying to learn.
learn. Yeah, that's right, Will. Yeah, I forgot about this meeting, and those girls will be waiting for me. So I will finish this later and I'll post it. And this is a long recording, so let me see if it's still recording with me. Yes.